Hello. So this is the eighth lecture, I think. And last time we finished talking about discrete time signal spaces. Okay, and just to remind you, the output of that discussion was some set of, or some collection of spaces of discrete time signals. Okay. And so we had precise definitions for all of these things. So in all of these cases, T is a discrete time domain. That's the case we're interested in. And in all of these cases, we had precise definitions for what these spaces were, and we had enumerated some of their properties, algebraic properties and sort of analytical properties in terms of their attributes as normed vector spaces, okay? So this time, we'll begin what will be a lengthy discussion of continuous time signal spaces. Okay, all right. Okay, so let's all right, so let's just sort of get things started. Okay, so that's the setup. So I have a continuous time domain, and I want to talk about F valued signals on that time domain. Okay, and so a continuous time domain, of course, is just an interval. Okay. So let's think about how we might even get the discussion started here. All right. And let's do that by looking at how we did this in the discrete time case. Well, we didn't quite do it this way, but at the end of the day, what we did was we made the observation that this was a nice space of signals in a certain sense. So it was a nice space of signals in the sense that on this space, okay, so this was the space of signals with finite supports, so they're non-zero except on a finite subset. The space was nice because on this space you could define all of the possible norms, all of the p norms where p goes from 1 to infinity, including infinity, okay? But at least when the time domain was infinite, those spaces were, those normed vector spaces were not complete, okay? But then what we did was we talked about their completions, all right? And so one way to view what we did in the discrete time case was we started with some basic collection of discrete time signals, this one, and that space had certain characteristics that we liked, and the principal one was that all of the norms can be defined on it, and then we kind of proceeded from there. That's one way to think about what we did. Again, we didn't quite exactly do it that way. We started out talking about sequence spaces, but that motivated that way of thinking about things. Okay, so you start with some, sort of core collection of signals, and this is kind of a collection of signals that you want to be included in any set of signals of interest. And certainly in the discrete time case, it makes sense that any space of signals you want to talk about, they should contain these ones, right? So they should contain the signals that are, basically, if you want to talk about subspaces of discrete time signals. By including this, what this essentially means is that you're allowing signals in your space, all signals in your space, which are non-zero at a single point and possibly zero everywhere else. Because by taking linear combinations of those kinds of things, you'll get an arbitrary element of this guy. All right. So in the discrete time case, that was easy to motivate. Okay, in the continuous time case, coming up with the correct analog, and there's multiple choices that you can make here. Unlike in the discrete time case, where more or less this is the obvious choice. Okay, in the continuous time case, it's less that way. Okay, all right. So the first thing we need to do, therefore, need to find a core space of signals on, we choose an arbitrary time domain T. And for that time domain T, you want to find some collection of signals that you want to be contained in any other collection of signals that you'd like to talk about. Okay. Okay, so what might this core of signals be? Okay, so this is the analog of this space of functions with finite support. Okay, so what properties? Okay. Well, so I'm going to sort of list some in, naive attempts to sort of see if we can come up with an answer to this question. And again, you might ask this question and come up with a different answer than I'm going to, but in some sense, any reasonable answer will be equivalent to the one I'm going to give. Okay, so you would like continuous signals to be in there. Okay, so your basic collection of signals should contain continuous signals. All right. Why would that be? Well, among all of the, so remember, continuous here is continuous in the analysis sense, not continuous time. Okay, so we have a continuous time domain, and on that continuous time domain, we have continuous signals in the epsilon delta sense of continuity. Okay, and so the idea is continuous signals are the nice ones, right? So you want your spaces to include the nice signals. All right. The other attribute you'd like, and this is analogous to why this space here was the appropriate core for discrete time signals, is you want all of the norms to be, the P norms to be defined on there. Okay, so would like all P norms Okay, so what are those P norms? There's the integral P norms. So we talked about these when we talked about norms, right? So we had norms on the space of continuous functions on the interval 0, 1. Okay, and so we saw that there were 3 norms there: the 1, the 2, and the infinity norm, and the the 1 and the 2 norm were special cases of a more general class of norms, which we called the P norms, where P is from 1 to infinity. Okay, but so that was on the interval 0, 1. Here we're just going to extend that to be signals defined on some arbitrary continuous time domain T, and the norm is the obvious adaptation of the norm on the interval 0, 1, like so. Okay, so that's the integral version of the integral P norms. Okay, for P less than infinity, and then of course there's also the infinity norm. Okay, so you would like for all of these norms to be defined on your signals. Okay, so these two requirements are in conflict. Okay. At least some version of them is. So this I think we can let's declare that we want this no matter what. Okay. So given that we'd like to impose this, is it possible to also impose this? Well, I didn't quite say which continuous signals I want to be included, but certainly you can't, for example, say all continuous signals. Okay. So if we require 2, it may not be possible to achieve 1. Get my handwriting in the sense that there may be continuous signals with P norm not defined. And this may be true for some P or for all P. Okay. So let's just give a, this isn't exotic. So for example, if T is equal to, let's say, just to choose something, the open interval or the closed interval from 0 to infinity, and with f of t equals t, let's say. Okay. Now, this is continuous, obviously, right? But none of these norms will be well defined for this f. Okay. And like I said, it's easy to come up with examples of f's that are maybe defined for some of these, but not all of them. Okay. And those are the kinds of things we'll be talking about later on. Okay. So therefore, if we're going to require 2, we have to restrict 1. Okay. So we restrict one by asking that continuous signals in our core have compact support. So I'll say what that means. Okay, so the support of F, which is now going to be some arbitrary signal. So it looks like an O. Okay, so suppose I have F, which is some arbitrary F valued continuous F valued signal on my time domain T. Okay, and what I want to do is I want to define the support of F. Okay. So what I do is I call it the support of F. Okay, and I take the set of all points where F of T is non-zero. Okay. Then I take the closure of that. All right. And then I intersect that with the time domain T. Okay. So this closure here means the closure is a subset of R. Okay, so this is going to be, these T's are in T, and so in particular they're in R, and so I'm taking the closure of a subset of R, and then after I take its closure, then I intersect it with T, and we'll see the relevance of all of that as we go along. Okay, all right, and so therefore we denote C0. Oops. C0 CPT. So these will be continuous signals on the time domain T with values in F and compact support. Okay. All right. So this, let's decide, is going to form our core of signals. Okay, and this should be thought of as being analogous to C finite in the discrete time case. Okay, so there, we've made a decision. Okay, it may be the wrong decision, but it's not, or else I wouldn't have showed it to you. Okay, but there's some obvious questions that you can ask about this space, and we will answer the questions, at least the ones that I'm going to give. Okay, so questions. Is it actually true that the P norms are well defined? On Okay, so this should be true for every time domain. All right, it is true, and we'll see why. Okay. What is and so the first question we'll ask is algebraic in nature, and that is, what is the dimension of a space of continuous time signals that contains our core? Okay, so we're going to be looking at spaces of signals that are bigger than that. And so any space which is bigger than that, what's its dimension? Okay. Okay, so that's kind of the algebraic structure of these spaces of signals. What about their analytical structure? Okay, so in terms of the norms. All right, so first of all, the answer to question one is going to be yes, and we'll see why. And so therefore, this question makes sense. Okay, so completeness, as we talked about last time, is an important property for a normed vector space to have. And so, yeah, I'm sorry, I often forget to do this, and I did this time. There's some terminology here which is important, because I'm going to maybe want to make reference to it. So I'll just scratch it down here and then erase it. So complete normed vector spaces are important enough that they have a name. They're called Banach spaces. Okay. All right. So when you ask if a normed vector space, excuse me, is sorry, is complete, what you're asking is it a Banach space? Okay, so this is the fact that these things have a human name attached to it suggests that they're important, and indeed they are. And the initial work on the subject of Banach spaces was done by the Polish mathematician Stefan Banach, sort of starting in the 30s, 1930s. Okay, all right. So Banach space. There's some terminology that we can use. Okay. Okay. All right. So let's think about this question for a second. So the answer here is going to depend on P. Okay. And it's also going to depend on the time domain. All right. So we're going to see that in fact, there's only really one case of one P and one T for which this space is complete. And for all others, it will not be. Okay. And so for all those others, what are the completions? Okay, and typically the difficulty of that question sort of splits into two cases. One is when p is equal to infinity, and then what we're going to see is that the completion of this space is relatively easy to understand. Moreover, it's something you can easily get your hands on, okay? Because it'll turn out that in the case of p equals infinity, the completion of this thing is another space of continuous signals, okay? The difficulty that arises is when p is not infinity. So in the case of the integral norms, the completion of this is actually quite complicated. Okay, and in particular, it doesn't really. The completion is not really a space of signals. Okay, it's a space of equivalence classes of signals, and we'll see exactly what that is. Okay, all right, so these are the questions that you can ask when you start thinking about continuous time signals. Okay, and we'll answer them. All right, so let me maybe first make sure that our restriction of continuous signals with compact support really does ensure that these norms are all defined, because that was one of our requirements. Okay, so answer 2, 1. Okay. All right. So we're going to let T be a continuous time domain. And we're going to let F be a continuous signal with compact support. And we're first going to look at the case of the integral p norms, so p going from 1 to infinity without including infinity. Okay. Now, so since F has compact support, there exists some k in the time domain T compact such that f of well, t is equal to 0 for t outside k. Okay, so then, all right, so I want to show that this is finite. Okay, well, because t is 0 outside k, this is the integral over k t p dt. Okay, now because f is a continuous function on this compact set, okay, well, certainly its restriction to the compact set is a continuous function on the compact set, and outside the compact set it's 0. But the point is that on the compact set it's continuous, and therefore it's bounded. Continuous functions on compact subsets are bounded, and so therefore there's some m, so that okay, So here I'm using the fact that continuous functions on compact sets are bounded. Okay. All right, so this is less than or equal to therefore m to the p integral over k of the function 1 dt. Okay, and so k is a compact set contained in the time domain t. And so therefore, there's going to be some compact interval AB, so that k is contained in AB. Okay, and the compact set AB is going to be can be obtained, for example, by taking A to be the infimum of the points in K, and B to be the supremum of the points in K. And because K is compact, actually these infimum and supremum are actually contained in K. All right, but that the only thing I really care about is this. And all I really care about is that this is finite. Okay. Okay, good. Now on p equals infinity, well, I've already done the p equals infinity case. Okay. Just by this fact that I've already used, that continuous functions on compact sets are bounded. Okay. All right, so the p norms are defined. Okay, that's good. What about the algebraic property? Okay, so what is the dimension of a continuous time space of signals containing this space of continuous compactly supported signals? And I'm going to show that as long as the time domain t isn't a single point, okay, so it has a non-empty interior, then the dimension of this thing is always infinite. Okay, so answer 2, 2. All right. Okay. So if the interior of T is not empty, and again, this just excludes the case of a continuous time domain, which doesn't consist of a single point, and that's not interesting anyway. And in that case, that the continuous time domain is also a discrete time domain, and moreover, it's a finite discrete time domain, and so we know then that its dimension is finite. In fact, its dimension is 1. Okay, but let's look at the only interesting case for continuous time domains, which is that one. Okay. And so I claim it's, so we talked a little bit when we talked about dimension. The only thing I'm interested in specifically about in this course as concerns dimension is whether it's finite or infinite, and it's always infinite in this case. So to see why this is true, we're first going to consider a special case. And so T is has a non-empty interior. And so I know, therefore, that there's some closed interval which is contained in T. That's definitely true. Okay, and my special case is that I'm going to assume that closed interval is the interval 0, 1. All right. All right, but we've already shown here that the space of compactly supported signals with which are defined on the interval 0, 1, we've already shown that that one is infinite dimensional. Okay, and how did we do that? We did this by, we didn't talk about this at that time, but now that we look back on it, we can make use of that fact. That we had signals defined on here, which were these sine functions, and we showed that there was an infinite collection of sine functions which were linearly independent. Okay, so we showed that the functions f, j, c 0, 0, 1 and these were defined by f, j, j of t. We used x then, but that's okay. 2 pi j t are linearly independent. This is one of our examples of a infinite linearly independent set. Okay. So we have to think a little bit to make sure that that actually gives us something useful here. Okay. So now, if 0, 1 is contained in T, then the FJs extend to signals in C0 CPT. Okay, and I'll illustrate that with a picture. So the picture is this. Okay, so here's, let's say, my time domain here. Okay, so that is T. And sitting inside T is the interval 0, 1. All right. And so these FJs, what do these FJs look like? Well, F1 was a sine function of a single period, like so. F2, like this. Okay, and so on. Okay, now the crucial thing here about these signals that makes them valid for the conclusion that I'm trying to reach is that there's 0 at the endpoints here. If I'd worked with cosine functions, then they would have had the value 1 at the endpoints. Okay, they would have looked like it would have looked like this. Okay, and these ones I could not extend to continuous signals on the entire time domain because if I took them to be 0 outside, they would now be discontinuous. Okay, so it's the fact that these things were 0 here, which allows me to extend them to continuous functions with compact support. Okay. All right, and so therefore, since the FJs are linearly independent, on when you restrict them to 0, 1, and 0 outside 0, 1, they are linearly independent as signals on, oops, the entire time domain. Okay, so I'm saying something there, and you should think about why that's true. Okay, so the point is that, by things that I previously did, if a time domain satisfies a condition like that, then it's automatically infinite dimensional because it contains this infinite collection of linearly independent signals, which are 0 outside the interval 0, 1, and then there are these sine functions inside 0, 1. Okay, now there's the general case. And in general, we can't assume that because the interior is empty, we can't assume that 0, 1 is contained in there, but certainly some compact interval, A, B, will be contained in T. Okay, so that's the general case. And this follows in the same way, basically. The picture looks exactly the same, except I have A here and B here. So I just have to, revise the argument of my sine function to make sure that it's, the function defined on the interval 0, 1 is now defined on the interval AB. Okay, I'm not going to explicitly write down how to do that, but you can easily see that that can be done. So we can argue as above by shifting and translating, shifting and scaling, shifting and translating are the same thing. AB into 0, 1. Okay. All right, so that answers 2, which is that essentially, except for the degenerate cases where that doesn't hold, we're always going to be talking about infinite dimensional spaces when we're talking about spaces of continuous time signals. Okay. All right. So now there remains the questions 3 and 4. Okay. And what we're going to see is that these spaces are complete in one case only. And that's the case where the time domain is compact, okay, and P is infinity. Okay, in all other cases, this space will not be complete. Okay, and then we need to talk about its completion. And the discussion of the completion is going to break down into 2 situations, one for P equals infinity and one for the rest. Okay. All right, so to answer 3 and 4, we will consider separately. The cases p equals infinity and p between 1 infinity. Okay, with this case being significantly easier than that case. All right, but that's going to take us some time, so we'll pick that up next time.